Okay, now it's 3:59, so let's start seminar. Uh, Today's seminar, the speaker is Jae Hyeok Chang, and he will talk about dark solar wind. Please start when you're ready.
Thank you for the invitation. I'm Jay from Johns Hopkins and University of Maryland, and today I'm going to talk about our work with Hopkins people, which called dark solar wind. Hey, let me start. So as we all know, dark matter exists. There are a lot of evidence, including galaxy rotation curves, black cluster, gravitational weak lensing images, and most importantly, the power spectrum of cosmic microwave background. And this power spectrum CMB tells us the contents of the universe, what is made of. And as we all know, around 70% of the total energy of the universe is dark energy, and like around 27% of the energy is dark matter, and only 5% is ordinary matter we know, which we understand very well, composed by standard model. However, the other 85% of the matter, we know almost nothing. But of course, we are particle physicists, so we want to figure what this dark matter is. And there are a lot of candidates, but most strongest candidate is WIMP. WIMP stands for weakly interacting massive particle, and this is a simple extension to the standard model. So we have our standard model, which is gauge group is SU3 cross SU2 times U1, and WIMP is just one additional particle charged under the same gauge group. So this is like the most simplest extension to the standard model. But surprisingly, this simple extension predicts the correct Rayleigh abundance today with just weak scale mass and weak scale coupling. So this was called WIMP miracle, and this explains two differences, dark matter, and this WIMP explains is the correct dark matter with very simple extension. So this was one of the famous dark matter candidate. So there are a lot of efforts to find WIMP. It cannot be seen very well, but there's a shaded region here, and there's a lot of dashed lines. Shaded region here is already excluded region in terms of the dark matter mass and the dark matter Euclidean cross section. So this is from the direct detection, which you search for mostly WIMP. But most of the parameter space is already ruled out. So, and we have the neutrino floor, where we have a lot of neutrino background, so we cannot see this dark matter particle in the direct detection. So we have only a very small gap left. And actually, this simple detection extension is already well above here, is already ruled out. So if we still have this WIMP, we need to think about more complicated model, not just this simple extension. So there's no signal for WIMP yet. So we can think about a more complicated model now, not just simple extension to the standard model. Now we can think about dark sector. So for the standard model sector, as I mentioned, this is made by this gauge group SU3, SU2, U1. And for the dark sector, can be not just a simple extension to the standard model, or it can just have its own gauge group. So dark sector also contains a lot of particles, and they have their own interactions. And one or a few particles in the dark sector can be dark matter. Then this dark sector and standard model sector are separated, but we can still see the dark sector particle through polar interaction. So this dark sector is natural to assume because we know only 5% of the energy has this much complicated model. Well, and dark matter is like 27% of the energy, but it's a little unfair to assume that's just one particle. So I think this can be enough motivation for dark sector. But still, we can see the dark sector particle through the particle interaction with polar. And polar is the gauge invariant and renormalizable terms that both include the standard model particle and the dark sector particle. There are three well-known polars. First, scalar polar is if you have the scalar particle in the dark sector, then we can write this term. This is our own Higgs. And Higgs square is, as we all know, this is gauge invariant. And if there's a similar particle in the dark sector, we can write this term, which is totally gauge invariant and renormalizable. So this term should appear in the Lagrangian with coupling kata. Then dark sector particle and standard model sector particle can interact with each other through this polar, this scalar polar. And if dark sector particle, this dark sector scalar is a real scalar, we can also have this term which with the dimension for coupling. And if dark sector has a singlet fermion, then we can write the neutrino polar. Then here N is just like a pseudo neutrino, and this similar form can have the for the dark sector, and then standard model sector, dark sector can interact with each other through the neutrino polar. And if dark sector has a U1 gauge group, which is simply a gauge group, and so very plausible, then as we all know, the field strength of U1 gauge boson is gauge invariant itself. This is hypercharged field strength, and this is gauge invariant itself. So this term B mu and F mu prime, this is field strength of the gauge dark U1 gauge boson, and then this term is also gauge invariant. So this is called vector polar. So we have these three well-known polar. So through this polar, we can search the dark sector particles. Here, I mean dark sector particle doesn't need to be the actual dark matter we have. This can be any particle in the dark sector because dark sector has a lot of particle interactions. So we our goal for this talk is looking for dark sector particle regardless of the actual dark matter. I can classify dark sector searches by 4 different groups according to the mass of the dark sector particle and coupling between the dark sector and the standard model sector. This is 4 different groups, and here in this region where mass is very small and coupling is very large is actually already ruled out region. In this region, then it's very easy to find, and so if this is true, then we should be able to see this kind of particle in the LHC and any other collider experiment. But we haven't seen anything so far, so this is ruled out region, and we can go to the right or to the bottom. This direction is a little hard, so I talk about this region and this region. And for the high, we haven't seen the dark sector particle just because mass is very heavy. This is one possible scenario. Then we need higher and higher energy. So we just LHC just don't have enough energy to produce this particle, and we need to build more powerful collider to have the much higher CM energy, then we can find this kind of particle.
I have a question.
Sure.
In the ruled out region, usually, as far as I know, this is just due to the resolution of experiments. We can think because of that we have not seen the particles in that region. So can we surely think that this region surely ruled out?
So of course it depends on the model and everything. This is just very simplified feature. But if coupling is large enough, then mass is small enough, then like somehow we should be able to see this.
The arrow line is
yeah, this is
over.
coupling. Yeah. Coupling between standard model particle and the dark sector. Yeah. So, but yeah, as just pointed out in this region, for this region, we have the enough energy to produce this particle, but just coupling to the standard model is very small. So it's just hard to see. It's hard to produce this kind of particle. And for this region, we don't need high energy. Instead, we need high luminosity to see this kind of particle. So in this talk, I'm going to talk about this region where the light dark sector searches. Okay, light dissector searches. So how do you prove the light dissector searches? Like as I mentioned, we need high luminosity, and for the mass between MEB and GeB, we normally use beam dummy experiment. Beam dummy experiment is you shoot a lot of proton to a target, and this proton produce a lot of pions, for example. And for a specific model, pion can decay to this dissector particle, and this dissector particle can decay another dissector particle. And there's the shielding. So this is a lot of like standard model particle is cannot penetrate this shield, but only dissector particle can penetrate this. So if you see some signal in the detector way far from this target, then maybe the dissector particle signal. So this is one way to produce this kind of particle, but this is very rare event. So you need a lot of protons to shoot this target, but you don't need a lot of energy. But for normally this kind of experiment has around GeV level proton beam energy, so you can probe around that up to that mass of the particle. However, if mass is even smaller than MEB, we can use stellar objects instead of the beam dummy experiment. Inside the stellar object, there are a lot of particles that keep colliding with each other with higher energy around their core temperature. For the supernova, core temperature is around 10 MeV, and for red giant or the sun, core temperature is keV energy. So if dissector particle is lighter than this core temperature, then they must be produced from the core of this stellar object, and we can use those particle, the produced particle, to observe this kind of new dissector particle. Of course, we do need this particle have the interaction with the particle in the standard particle in the stellar object. But once they have stellar inside the stellar, there are so many particles, so we can have like a lot, like very huge luminosity to prove this. So, and as you expected from the title, I can focus on the sun in this talk. Okay.
How about neutron star?
Neutron star, of course, neutron star is similar to the supernova, or which is not the same, but like neutron star also has like core temperature around 10 MeV, so of course you can use neutron star as well. But in this talk, I'm going to focus on the sun. Okay, let's see the particle production from the sun. And say this is our sun, which has core temperature around keV, and this is the Earth. Then if we have the dissector particle that is lighter than keV and has the coupling between with some particle inside the sun, such as proton, neutron, electrons, or photons, then they must be produced inside the sun, and they can free stream to the Earth. Then we can look for this kind of particle in the Earth, and this is like one basic mechanism to look for dissectors. And for this kind of search, let's assume what's the maximum flux of this kind of particle at the Earth. And to determine this, we need to see the luminosity of the dissector, and actually luminosity of the dissector, we have the upper bound. Because this kind of particle carry energy from inside the sun to the outside. So each particle contribute to the cooling of the sun. So if we have like too many particles that carries energy from inside to outside, then actually this accelerates cooling of the sun. Then that changes the evolution history of the sun, and our sun should be different from what we have observed. But our sun is perfectly agree with the standard model prediction, their lifetime and their temperature today, everything agrees with the standard model prediction. So we can conclude that we don't have like this kind of particle that carries a lot of energy. So this gives a cooling bound, cooling argument mostly established by George Raphael. And from this Raphael criterion, we see dissector luminosity from the sun should be less than 1% of the total solar luminosity. Otherwise, this particle messes up the evolution history of the sun. So this is our upper bound of the dissector luminosity, which is 4 times 10 to the 31 erg per second.
Is the 1%? coming from some rigorous calculation or just a 1%?
So this mostly from the simulation, that's true, but actually this 1% is not from the sun. This 1% of the sun luminosity is from the red giant. So for the red giant, it gives a stronger constraint compared to the sun. But if you convert to the solar luminosity, this is becomes 1%. But if you compare to the red giant, it is not that 1%. It's just like similar to the luminosity of the red giant. Okay, so flux of this particle can be easily calculated with this equation, LD divided by 4 pi d square, and E here D is the distance between the sun and the earth, which is just 1 AU, and E is the average energy of the particle, which is around the core temperature, keV, and we can use the maximum luminosity for this to get the maximum flux. And this is 10 to the 13 per centimeter square per second. You may think this number is a very, very large number. If you have just 1 centimeter square area, then 10 to the 13 particle can pass through this area per second. But actually, this is not enough flux to detect this kind of particle. Because of the cooling argument, this particle should be should couple to the standard particle very weakly. So the cross section between the standard particle and this particle is very, very tiny. So even if you have this many particles, then this is actually not enough flux to detect this kind of particle. So we need more flux to see this kind of the particle from the sun at the earth. Okay. Then so far, I have assumed these particles are free stream to us after produced from the inside the sun. But what if we have this particle, dioxide particle, have strong interaction by themselves? This particle cannot have very strong interaction to the standard particle because of the cooling argument, but there's no constraint on their self interactions. So now from now on, we can assume this dioxide particle has very strong self-interaction strength, and they have a number changing process. Let's say this is 2 particles produced from the core of the sun, and then average energy of each particle is roughly temperature of the sun. And due to their strong interaction, they can find each other very easily, and they can go to 3 particles because of the number changing process. This is easily happen if the mass of the particle is much smaller than their average energy of the initial particle. Then for the final state, the average energy is smaller, and due to this small energy, they can even easier to find each other, and they can interact, and the energy is even smaller. So they keep doing this until they are fully thermalized. So they easily thermalize each other by producing a lot of particles, and they form thermal equilibrium by themselves. So this plasma have direct temperature, and this direct temperature is actually different from the standard model temperature in the sun, because the standard model sector and direct sector are thermally decoupled, but standard model plasma and direct plasma have thermal equilibrium by their own. So what we get after with this strong self-interaction is self-thermalized plasma. And when they form this self-thermalized plasma, they have pressure, and this pressure boosts this plasma itself, and they are accelerated. So what we see from the Earth in this case is relativistic steady outflow, and we call this outflow as direct solar wind. Okay. Now, let's assume the flux of the direct solar wind. So this is for comparison the previous calculation for the flux for the free streaming case. And now we can calculate the flux for the direct solar wind. And for here, maximum luminosity and distance is of course the same, but average energy is actually different. Average energy, I can follow the similar calculation to the solar surface temperature, and assuming they have thermal equilibrium inside the sun, and what we have is around 0.1 eV per particle. Then a flux of the dark solar wind is actually 4 orders of magnitude larger because we have 4 orders of magnitude smaller energy per each particle. So instead of like a few very energetic particle, in this case, if they have strong strong self-interaction, we have a lot of particle with smaller energy. So if we are sensitive, if we have a experiment like direct detection experiment which are sensitive to this very small energy, then we can take advantages of this 4 orders of magnitude larger flux. Sure. Yeah.
That is independent of the self-coupling strength.
Yeah, as long as they form thermal equilibrium, then it doesn't matter. So yeah, once they form the thermal equilibrium, their dynamics is explained by their own temperature and their own the bulk velocity, and doesn't depend on any detailed dynamics.
Because you remember the fraction of document in the sun.
Fraction of the document in the sun, which means like here we need to produce the particle from the sun, not they are not the documented particle, but that depends on the like how many particles are produced some in the initially. So that depends on LD. That LD determines that. So this is the only the maximum flux from the cooling argument. But of course, if the total energy of the dissected particle is smaller than the maximum, then of course we have less particle flux.
And then generically by requiring the less velocity, you mean that dark particles are cooler than?
Yeah, dark particles are much cooler than the standard model case. I'm gonna show you the exact number later. Okay. Okay, so a very brief summary of the introduction. We can dissect particles can reach to the Earth in forms of boosted dark plasma if they have strong self-interaction. And this predicts 4 orders of magnitude larger flux compared to the free streaming case, and it encourages new experimental direction, which is very sensitive to the smaller energies. Okay, then now we can talk about what dark sector model can form this dark solar wind. There are several conditions to have this dark solar wind. First condition is, of course, this dark sector particle needs to be produced from the sun, inside the sun. For this, we need a coupling between this dark sector and standard model sector, especially proton, neutron, electron, or photon. But this coupling should be smaller than the cooling bound. Cooling bound is actually very strong constraint, so we need to consider this stellar bound like for when we consider the particle production from the stellar object. Okay, this is first condition. And second condition is self-thermalization. This particle needs to have the thermalize with themselves. So we need the number changing process for the chemical equilibrium, and self-interaction should be strong enough to have the thermal equilibrium inside the sun. And and we need to have the relativistic fluid, and they need to be relativistic even after the thermalization, because we have assumed the thermal distribution. So we need to have this dark sector particle should be very light. Okay, and the model I'm going to talk about this talk is the millicharged particle model. Of course, any dark sector model that satisfies the 3 conditions can have the dark sector model. I just pick one well-known model, and I'm going to show you.
Slow, but then your third assumption about relativistic. Why do you find that?
So this is actually a little complicated. So if it's not relativistic, then which means the dark sector temperature is actually lower than this particle mass, then they are not in the thermal equilibrium. They are annihilated with the other, and they just start to free stream. So of course, if you have the chemical potential like the standard particle in the sun, then they can still have this thermal fluid. But if like this is dark sector particle, so unless we have some connection between baryon number density and some dark sector number density, then dark sector particle doesn't have this chemical potential, and they are annihilated with each other. and then their number density becomes very low, and then the number density has not enough becomes not enough to maintain the thermal equilibrium. But of course, we can. This is not very strict condition. We can think about some model that has even non-relativistic fluid, but that applies only very specific model. So for the generalization, I just include this, and this makes the life much easier. Calculation is much easier. So yes, strictly this is not a condition, but generally we do need this. Okay. So I just choose the well-known millicharged particle model. Here we have two particles, which is dark photon, which is a gauge boson of U1 dark, which is mixed with standard model photon in the low energies. And we have millicharged particle, which is a fermion charged under U1 dark. Then in this case, this millicharged particle can interact with the charged particle with charge epsilon times the electroweak coupling E. That's why this model is called the millicharged particle model. And I'm going to see if this model satisfies all the conditions. And we have three model parameters, which is mass of the millicharged particle, epsilon, which determines the strength between the standard model and the dark sector, and alpha dark is the self-coupling fine structure constant for the dark sector. Okay, let's talk about the easier one first, relativistic fluid. We can just assume millicharged particle is effectively massless, means mass is smaller than any other scales we consider inside the sun. So core temperature of the sun, the plasma frequency, every physical quantity we can imagine, just millicharged particle is much smaller than that scale. Then millicharged particle is effectively massless, and we can start from the massless case, which is always relativistic, and we can mention the massive case later. Then remaining parameters are epsilon and alpha dark. Okay, production from the sun. For the millicharged particle, the dominant production process from the sun is plasmon decay. So photon inside the core of the sun has actually gets a photon thermal mass from the hot and dense fluid. And so this photon mass is roughly the order of plasma frequency of the sun. Then this plasmon can decay to a pair of charged particle. Then this photon can also decay to the millicharged particle through this kinetic mixing. And actually, this is the dominant production mechanism for small mass millicharged particle. And actually, this is the dominant production for the neutrino inside the supernova as well. Through the Z boson, and it goes to the neutrino, and anti-neutrino is the dominant production. But
excuse me. Then which one is really dark matter?
So here I'm not talking about the dark matter. These are the dark photon, and these millicharged particles are just dark sector particles. They don't need to be the dark matter. So I'm talking about the dark sector searches, not actually dark matter searches. So they are produced from the sun, so they don't need to be the dark matter. I'm not using any fact that they exist, like they have relative abundance today. So the production rate is proportional to epsilon square alpha dark. We have one epsilon from the vertex and one ED from this vertex, and V square to have the rate. So the production rate is proportional to epsilon square alpha dark. Okay, then, sorry?
What is the case?
K is just the momentum of the photon. So for this is transverse energy of the photon, and this is the momentum of the
Momentum.
Yeah, this is three momentum of the plasma. Yeah. So for this case, transverse mode actually dominates. So longitudinal mode is suppressed. Okay, and as I mentioned, we need to consider stellar cooling bound, And most stringent constraint for small mass millicharged particle is actually, as I mentioned, from the red giant. If there's an extra cooling for the red giant, and that delays the helium ignition and make the red giant brighter than expected. But we haven't observed this kind of red giant. We always see red giant agree with the standard model expectation. We can put constraint, which is this number. So this is our parameter space. We assume mass is very small, so remaining parameter is epsilon and alpha dark. And from the cooling bound, we lose this parameter space. So above this line, this is ruled out from the red giant cooling constraint. So we consider only the parameter space below. And the second condition, self-thermalization. After these particles are produced, they need to have the strong self-interaction and they need to be self-thermalized. So, and this is well studied in the reheating scenario, because after inflaton decays, we have a few very energetic particles from the inflaton decay, and they are thermalized after the inflaton decay and form the thermal plasma of the radiation. So, and for this, I can just follow the study of the reheating scenarios, and number changing process plays most important role for this thermalization. And in our case, the Bremsstrahlung of dark photon is most relevant process, which is this. So we do need a number changing process of the dark sector particle, and you can see 2 dark sector particle goes to 3 dark sector particle here. And we require this rate of the 2 to 3 process should be larger than some scale. For the inflation, this is Hubble, but in our case, our relevant scale is the inverse of the core radius. And actually, this calculation has a lot of interesting feature, but I don't think I have enough time, so we can discuss about this after the talk, if you're interested. And
Core means the core of sun.
yeah, core of the sun. So I assume this particle needs to be thermalized before leaving the core of the sun. So that's our one criterion. So inside the core is particles are mostly the profile, electron profile, temperature profiles are mostly flat. So as long as they are thermalized inside the core, then they can maintain this self-thermalization even after even outside the core. So from this, we have this number requiring this number changing process rate is larger than our relevant time scale. Okay, from this, we have this line. So below this line, we don't have enough self-coupling between the dark sector to be fully thermalized before leaving this core. So we do need large enough self-coupling, but you may wonder why this line not only depends on alpha dark, which is self-coupling, but also depends on epsilon, which is a coupling between standard model and the dark sector. The reason is if you have larger epsilon, means you produce more and more dark sector particle from the sun, because the coupling between standard model and the dark sector is larger, and more and more dark sector particles are produced. And if you have more number of this particle, then it's easier to be thermalized. Even for the same, even with the same self coupling, if you have more number of particles, then it's easier to be thermalized. That's why this line also depends on epsilon as well. So above this line, we have cooling constraints, so we cannot have this parameter space. And below this line, we don't have fully thermalized plasma in the dark sector. And so similar, in this case, similar to the just free streaming case, and we only consider between these 2 lines where this dark sector particle can be fully thermalized before leaving the sun. Okay, then now we can talk about properties of this dark solar wind inside the parameter space. Okay, in those parameter space between 2 lines, there's the parameter space where we can guarantee dark sectors are fully thermalized. Then for the fully thermalized plasma, pre-pass is small enough, so we can assume it's a perfect fluid of the dissected particle. Then energy momentum tensor of the perfect fluid is expressed with this equation as usually, with the energy density and pressure is determined by dissector co-moving temperature, and this U vector is full velocity vector with gamma. So this co-moving temperature, I can assume this is a spherical symmetry because these are produced from the sun. Then this DAX fluid is fully determined by the co-moving temperature and their birth velocity, gamma or V. Gamma is, of course, the 1 over square root of 1 minus V squared. So if we have the temperature and gamma, then we can fully determine the properties of this plasma. Then we can solve the continuity equation with the source term. The source term is the energy injection from the standard model to the dissector. This T mu is only for the dissector energy momentum tensor, so there is energy injection from the standard model, which is proportional to epsilon square alpha dot. But there's no momentum injection because this production is more like isotropic. So we only have the energy injection, and if you solve this continuity equation, we can have our two master equation. I call the first equation as a temperature equation and second equation as a velocity equation. Because if you solve this equation, you can fully determine the velocity of this plasma. And if you put velocity here, and you can determine the temperature.
Sorry. So you neglect the potential in your.
So you mean gravitational potential?
Because you're assuming.
Yeah.
Hydrostatic equilibrium is maintained by baryons.
Yeah. They're not from the area. Their fluid is maintained. They don't need to be actually trapped. They're going outward. So there's no trapping. But actually, we can. Yeah, it's not trapped fluid. They are just moving outward. But in principle, we need to include the gravitational potential in the metric, and we have tracked. The gravitational potential is actually much smaller. It's negligible because the pressure of this plasma is larger enough. Yeah, right. So it's negligible. We have checked that. So okay, so let's see the velocity equation first, and this is the radius in terms of the solar radius, and y-axis is just number. And here is around the Earth's orbit, which is around like 200 solar radius. So if you solve this equation where Fr looks like this is Fr is model dependent, but the detail is model dependent. But for any model that has taxonomy, have the universal feature, which is order 1 in the core and drops quickly as you go to the surface of the sun. So with this Fr, you can solve this equation to determine the velocity of this plasma. But you need to be careful because at the sonic point where the velocity is the sound speed, this equation blows up because of this term. So to pass through this sonic point smoothly, actually whole right-hand side need to be 0. Otherwise, you cannot pass through this sonic point, and this is a well-known problem in the astrophysics. So at the sonic point where v equals to square root of there, this term should be 0, which means Fr should be 2 over 3. So this is a sonic point where Fr equals 2 over 3, and we need to have the velocity equals to the sound speed. So this acts like a boundary condition for this equation. So you can use this boundary condition, and you can solve separately inside and outside this sonic point. And this is a result. I expressed with gamma because we are more interested in the property near the Earth. So you have like non-relativistic this plasma. That particles are relativistic, but work velocity of this plasma is velocity is small, but it's accelerated as it goes outward. Okay, then we can use temperature equation. If you put this velocity equation to this temperature equation, then we can get the temperature. But this is parameter dependent. This gamma doesn't depend any parameter epsilon or alpha dark as long as they have perfect fluid. But this temperature actually depends on the source term. If you have like more energy injection, you have a higher temperature. So this is an example of the dissector temperature, dissector co-moving temperature for epsilon equals 10 to the minus 15 and alpha equals 1 hour Fiducial point. Then this whole process is actually very similar to the Parker's solar wind, the actual solar wind, but the solution is actually asymptote to the fiber solution from the gamma ray burst. As you can see, gamma is proportional to the radius at large radius, and temperature is inversely proportional to the radius. And this is exactly the same feature as the fiber solution. And in our case, this is for relativistic and adiabatic plasma, while the Parker solar wind is non-relativistic and isothermal plasma. That's the difference. Okay, so we are interested in more physical value, which is average energy of the particle and the number density of the particle to see this particle in the Earth. So average energy of the particle is given by gamma times T. So average energy of the particle in the co-moving frame is their co-moving temperature, but this is boosted plasma. So average energy in the rest frame or solar frame is gamma times co-moving temperature, which is case like constant. And number density is given by gamma times T cube. Is same that you have the T cube number density in the co-moving frame, and once you boost in one direction, you have the one dimension contraction. So this is proportional to 1 over r squared. So this scaling is actually same as a free streaming scaling. If particle has free stream, of course, energy density doesn't depend on energy of each particle. It's just conserved, and number density is just proportional to 1 over r squared because it propagates radially. But once it has a stack allowing the initial point, initial energy and initial number density is very different from the free streaming case. So we have much larger number density with much smaller average energy of the particle. Okay, so this is direct fluid profiles near the Earth. Gamma near the Earth is around 900, which can be as large as like around 10 to the 3. And co-moving temperature is around 0.1 millieV. Of course, this depends on epsilon and alpha dark. And average energy is roughly 0.5 eV, and the number density is around 10 to the 5 per cubic centimeter, which corresponds to 10 to the 17 per centimeter square per second, roughly. So in this our parameter space, I can show the properties of the diaxial wind. And near the cooling bound, we can have number density as large as 10 to the 5 per cubic centimeter, and average energy is 400 like millieV. And as you go below, and you have the less and less production, so you have less number density and less energy. Okay, and let me comment about the massive particle. And if you have massive particle, then actually what we have changed is this criterion. So if our particles are massive, actually it's harder to make thermalized. So gamma 2 to 3 in terms of some 1 over in unit of 1 over core radius actually decreases. So you need larger and larger alpha dark to have the thermalization. So for if the millicharged particle have 1 eV, then you have only this much parameter space, which is much smaller parameter space that can have this diaxial wind. However, as long as you have the diaxial wind, the properties of diaxial wind remains the same because properties of diaxial wind are fully determined by the continuity equation of the energy momentum tensor. So conclusions. Dissected particles can be produced from the sun, and if they have strong self-interactions, they thermalize and form dark solar wind, which is relativistic steady outflow. And this dark solar wind leaves unique phenomenological signatures near the Earth, which has more flux exchanging with smaller energies. So, and this encourages new experimental direction as you go to smaller and smaller energy, sensitive to the smaller and smaller energy. And there's can be many follow-ups, and we can think about actual detection sensitivities in the existing or proposed experiment. And we can think about other model other than the millicharged particle model. And we can even think about other astrophysical objects such as supernova. The main difference in the supernova is for the sun, we have only the energy injection, there's no momentum injection. But for the supernova, they have the explosion to the outward. So in that case, they also have the momentum injection. And this difference may leave some interesting features.
You mean non-isotropic?
This still isotropic,
Ah,
but
yeah, radially.
Radially,
Okay.
Okay, that's all. Thank you so much.
Thank you for very interesting talk. Is there any question?
So what's the energy loss rate per second per sun? I mean, U plus suggests that the sun
Yeah.
loses energy.
Right. So
Maybe, yeah.
it's very only here.
You said that at a
Yeah, it-
given time,
Mm-hmm.
that's 1% of solar house
Mhm.
depends on that. But then this happened from the beginning, so we have to multiply 10 billion years. No,
Yeah, the roughly age of the sun. Yeah.
multiply age of sun,
Mhm.
must be huge energy.
Yeah, there's huge energy. So like of course sun is keep losing energy with the solar luminosity, of course, by photon and neutrino, but mainly from the photon. But like if it's like say 0.1% of the solar luminosity, then that doesn't change the evolution history of the sun much. What we see, even though there's a huge energy, but what we see is same because the dominant energy loss mechanism is just through the photon at the solar surface. But if it's larger than 1%, then this is the energy, we can see some difference. So of course, that's a huge energy over huge time. But for these types of wind, they are not trapped near the sun. They are just free stream, not free stream, but they are just moving outwards. So they keep producing this energy.
Other questions?
I have a question.
Yeah, please.
Yeah, I want to know what kind of experiment can detect such a dark solar wind? Can you show me some example?
Yes. So actually, I wanted to include some detector sensitivity in this paper, but yeah, there are some difficulties. First, like our dark solar wind is made by both dark photon and the dark matter. These are the particles inside the plasma. So what we see is plasma of dark photon and dark matter. So first, we thought about the dark photon absorption experiment. There are several proposed dark photon absorption experiment assuming dark photon dark matter. So we naively thought the energy, if the energy of this dark photon is same as the mass of the dark photon dark matter, then we expected we have the similar sensitivity. But actually, this dark solar wind is a very unique phenomenological signature, which is boosted thermal plasma. So actually, when we detect the dark photon dark matter, then actually our dark photon mass is very small. Is dark photon thermal mass is order of the core temperature, not order of their energy. So the good co-moving temperature for this dark photon is like depending on the parameter, but for our fiducial parameter, roughly 0.1 like 1 millieV. And while the actual energy we see from the dark photon is one electron volt. If we have 1 electron volt mass dark photon, we can see this dark photon, but this is their plasma mass is around like millieV, but they are just boosted and they have this EV energy. So actually there are a lot of suppression, which is m prime over e to the square for the transverse and 4 to the longitudinal. So direct photon absorption is actually very suppressed for this specific case because of this is boosted thermal plasma. So we turn to the millicharged particle detection in the direct detection, like from the elastic scattering. But this is also very suppressed because these are relativistic particles. So their mass is also like very small, and their energy is still large. And when you think about elastic scattering, if you have very large velocity, then this is actually suppression because what it matters for the direct detection is the momentum, not the energy. So if you think about some dark matter, which has V is 10 to the minus 3, then their momentum is actually much larger by a factor of this much, 10 to the 3. But their energy, even if we have the same energy as this dark solar wind and the dark matter, then we still have this larger suppression. So in these two cases, we couldn't see very promising sensitivity, but we are expecting there can be some experiment which is non-elastic scattering, such as in the superconductor or like the superconductor is one example, and the other example can be some photon experiment, which is interaction with a whole atom and their dynamics. And we can also use their fluid. Their fluid is not as like a dark matter. They are just mostly there's a direction from the sun to the earth, while the dark matter is random direction. So if you think about that directional effect, then we can see this kind of particle in the some specific experiment, such as direct deflection. So this is like we are still working on it. We haven't get the promising sensitivity yet, but I think in the future, if there's more technology to see these small energies, then I think we can definitely take these advantages of huge flux.
Okay, thank you.
Thank you.
In terms of detection,
Mhm.
this dark solar wind have two component particles.
Yeah, right,
Dark photon and dark
right.
millicharged particle. Can you they are equally the number of particles are equally or they are different?
Yeah, this is just thermal plasma, so number of particle just depends on their degree of freedom and whether it's boson or fermion. So but they're all they all have this order. Yeah, those particles have all disorder, gamma times T to the cube, but due to their degrees of freedom, with dark photon has I assume massless dark photon, so 2 degrees of freedom, and for the fermion they have like 4 degrees of freedom. That's one difference, and for the fermion you have like additional 3 over 4 factor, but that's the only difference. They have roughly similar number density in the plasma.
So for the alpha D, why did you cover only up to 1?
So yeah, of course, like in principle, I can go to around 4 pi. But yeah, in principle, I can go to 4 pi. 4 pi is around the unitarity bound. But if alpha dark is even larger than 1, is not perturbative, right? So yeah, if we are a little shameless, we can extend the parameter space up to 4 pi, but I think we still have enough parameter space even below 1, so we cut here. But you're right, in principle we can extend this parameter space to the unitarity bound.
Can I see the next plot?
Yeah.
Okay. But you know that line,
Mhm.
right? that line is almost parallel.
Yeah, it's always parallel to this
Stand
line.
cooling.
Yeah, because this cooling bound is determined by how much energy is produced from the sun. And this is also determined by how much energy. Once you are thermalized and only quantity you have is what's the total energy of this dark particle production per second. And that's always proportional to the epsilon square alpha dark. Because of production mechanism, you have one kinetic mixing and one dissector vertex. So that's always the same scaling. So this different line determines the total energy production of the dissector.
Then, I mean, for the number density,
Mhm.
even though you go beyond the alpha D of one,
Mhm.
you don't gain anything.
Yeah, if you
Right.
follow this
Yeah,
line,
yeah,
everything is the same.
Everything is the same.
Yeah,
Okay.
the number density and in terms of number density and the average energy, then
Energy.
it's the same in this slope. Yeah.
Other questions? Actually, I have several questions, but this is very stupid level, so I'm going to ask you one. Actually, I can understand. Definitely, there are dark matter plasma, right? And also, we can consider all the we can consider the dark matter plasma in all the any stars, something like that. Then I think they should affect to the relic abundance.
Mm-hmm.
Yeah, I can understand about that.
Yeah. So, right, if you have a relic abundance of this kind of particle,
Mm.
then there's gonna be some this type plasma or any this solar wind from any other star can interact with the relic dark matter. That's actually true and interesting point.
Mm.
Here, when I calculate this, when I solve this equation, oh sorry, this is back of slide. Yeah, when I solve this equation, I assume there's no pressure of this particle. There's no relic particle. But if there's a relic particle, then there's a interaction between this difluorine and the relic particle. So there's a possibility that the solution actually boundary condition is doesn't need to temperature doesn't need to go to zero at the large radius. Then actually there's another solution is possible, which is subsonic solution, where velocity is always smaller than this sonic speed sound. Then in this case, we can actually have a totally different shape of the difluorine. But we haven't considered the relic density because this is very light particle. So if we have this relic density of this light particle from the thermal production, then this is already ruled out from the ineffective. So that's why we haven't considered. But if there's some non-thermal production and there's an interaction between this difluorine and the relic particle, then they can actually change the properties of the difluorine.
Oh, I see. Oh. Any other question? Yeah.
I have a question. So this solar wind is made of mini charged particle.
Yeah, and the dark bottom. So both of them.
What is the rough size of the current?
Sorry, the size of
Rough size of the electric current.
electric current. That's a good question. So we have the flux of this particle, right? So the number density, and then we have the millicharge. This is millicharge particle, but actually because of the cooling bound, our epsilon needs to be super small, around 10 to the minus 15. So if you have the electric current, then it's not that large. But yeah, but as I mentioned, for the detection side, they have this directional effect. So they have actually electric current. So if you think about similar to the direct deflection experiment, then actually that uses this electric current and bend this particle goes to a different direction up to the different due to the charge of this particle. So if you can see those differences, then you can actually see this taxonomy by measuring the electric current.
Any other question? If not, let's thank the speakers again.
Thank you.
And also we have a seminar dinner 6 p.m. Let's meet in the tea room at 6 p.m. Right? Okay.
How many people are going?
Maybe I need to ask now.
No.
Yeah, Berlin and Professor Go, Sanjoy.
Yeah.
And that interest to the.
Yeah. Shinyu, will you go to the seminar dinner?
Yeah.
Okay, I'll come to you in New York.
Okay. Thank you.
Yeah.
And
6 p.m. Yeah, 6 p.m.
how many people are going?
Maybe 1, 2, 3, 4, 5, 6. 6 people. That's 6 people.
So where did you go yesterday?
Prada. It's a
Oh.
chicken restaurant.
The
Six there.
Okay.
Yeah.
So where should I? So we today not chicken.
Okay, I got it.
Okay.
I'm going to ask you, speaker,
Yeah,
today's
yeah.
menu. Yeah.
Yes.
Yeah.
I'm okay, sir.
내일 저녁 있나요?
그게 없는
없는 거죠?
예,
네,
없는
네.
것 같아요. 예.
뭐가?
저녁
내일
클럽.
저녁.
이번 주에 세미나가 2개